Last time we looked at absolute maximum and absolute minimum values of a function on a closed interval. And we said that in order to find absolute maximum and absolute minimum values of a function on a closed interval, we need to check the endpoints and we need to look at the local maximum and local minimum values that occur at these critical numbers. That leads us into the closed interval method. This is the method or the technique we're going to use to find these absolute maximum and minimum values of a function on a closed interval. So here's the technique. We're going to find the values of f at the critical numbers of f in AB. If you recall from the last video, to find our critical numbers, we are going to set the derivative equal to 0 and look for those values of x where the derivative equals 0. Those give us critical numbers. And we're also going to look at where f prime of x, what values of x make the derivative undefined or it does not exist. Those two give us the critical numbers that we're going to be checking on this interval AB. So those critical numbers need to be falling in between this interval or we're not going to check those because those would fall outside the intervals. Second, find the values of f at the endpoints of the interval. As we discussed in the last video, we said that maximum and minimum values can occur at the endpoints. Here's our endpoints A and B, or they can occur at our critical numbers. So what we're going to do is we're just going to plug these values that we find from locating our critical numbers into the function along with our endpoints. We'll see what those values equal, and then the largest value will be our absolute maximum. So here from the graph we could see the absolute maximum would occur at B. And in this case the absolute minimum would occur at A, f of A. So that's what part 2 means. Find the values of f at the endpoints of the interval. And then part 3, the largest of the values is the absolute maximum value. The smallest of these values is the absolute minimum values. So it's a 3-step process. Find your critical numbers, identify your endpoints, plug those into your function, and the biggest value is your absolute max, the smallest value is your absolute minimum. Find the absolute maximum and minimum values of this function. Now we're looking at the interval -1/2 to 4. So the process, we're going to find where f prime of x equals 0, and we're going to see if there's any place that the derivative does not exist. So first of all, if we looked at f prime of x, that would give us 3x squared minus 6x. We're going to set this equal to 0 and solve. We can factor out a 3x solving for x, we would set each one of these factors equal to 0. So we would have a critical number at x equals 0, and we have a critical number at x equals 2. Looking at our derivative, is there any value of x that would make this undefined? No, there are no values of x that would make this undefined. Therefore, the only critical numbers we have are x equals 0, x equals 2. Both of those fall within our closed interval, -1 to 4. So we've found our critical numbers. And we've identified our endpoints. I'm just going to call that A is -1/2 and B equals 4. Those are our endpoints. So we're going to plug those values into our function and then just compare these values to find the absolute maximum value and the absolute minimum value. So I'm just going to put these in order. And that's how we determine our absolute maximum and absolute minimum values. That's the process. Now let's go ahead and find these values. So here's the process of finding our critical numbers. Here we found our endpoints. We identified the endpoints at -1/2 and 4, and when we plug those into the function, we get 1/8 and 17. When we plugged our critical values into the function, we got 1, and then when we plugged in 2, we got -3. So the largest value, which is at here, this is our largest value, 17. So our absolute maximum occurs when x equals 4. That is our absolute maximum value. That's where it occurs. And the value is 17. And then we look for the smallest number, which is here at -3. So when x equals -3, we have our absolute minimum value. And that value is -3. This is the closed interval method. Estimate the absolute minimum and maximum values of the function x minus 2 sine of x on the interval 0 to 2 pi. We'll be using the closed interval method. We do need to find f prime of x. So that's 1 minus 2 cosine of x. If we set this equal to 0, we could solve for x. We would subtract 1 and divide by -2. So we're thinking the cosine of what angle equals 1/2. So we could find our critical numbers. Now the cosine of pi over 3 is in the first quadrant. We know cosine is positive in this quadrant here and in the fourth quadrant. So since we have a reference angle of pi by 3, we know this angle here would be pi by 3. But to find that angle, we're going to say 2 pi minus pi by 3. And if we got common denominators, we'd have 6 pi minus pi over 3, or 5 pi over 3. So there are our critical values, or our critical numbers. Are there any values of x where our derivative is undefined? No, we cannot find any values of x that would make this undefined. So those are our only critical values. Identifying our endpoints, those are given to us here, so 0 and 2 pi. 6.28 was just an approximation for 2 pi. So we are going to compare the values f of 0, f of pi over 3, f of 5 pi over 3, and f of 2 pi. And we're going to look for the largest value for our absolute maximum. The smallest value will give us our absolute minimum. Those are our critical numbers, and those are the values of the extreme values. Those are the values of the critical numbers. Now our endpoints, and we can see the largest value is 6.96, which occurs at 5 pi by 3, and the smallest value is negative 0.685, which occurs at pi by 3. So we have identified our absolute maximum value and our absolute minimum value. And looking at the graph, there is pi by 3. We can see there is the minimum value, 5 pi by 3. That is our absolute maximum on the interval that we were discussing. I believe it was -1 to 2 pi. The Hubble Space Telescope was deployed on April 24, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at t equals 0 until the solid rocket boosters were jettisoned at t equals 126 seconds is given by. So here is the velocity function. Then it goes on to say find the absolute maximum and minimum values of the acceleration of the shuttle between liftoff and jettisoning the boosters. We are trying to find the absolute maximum and minimum values of the acceleration function. So in order to find the acceleration function, we would need to take the derivative of our velocity function. So our acceleration function is here. Now we don't want to set this equal to 0. We are trying to find the maximum and minimum values of this acceleration function. So we need the derivative of the acceleration function to find our critical numbers. So let's take the derivative again and set that equal to 0. So first of all, a prime of t. Here's the derivative of our acceleration, and if we solve for t, we get 23.12. Second, we need to identify our endpoints. And the endpoints were from liftoff, which is 0, to t equals 126 seconds. So we plug those values back into the acceleration function and compare those values. We can see the absolute maximum value, the maximum acceleration, occurred at 126 seconds. And the absolute minimum acceleration occurred at 23.12 seconds at our critical number.